Hello everyone, and welcome all of you to this episode number 15 of Project Discussion Series, an online series where we discuss projects, solve problems, and share new ideas, and get to meet and learn from young and experienced structural engineers. So, this is the episode 15, and hello to those who are watching it live, and also welcome to those who will be watching this episode later. So today we also, just like all our previous episodes, we have a power packed episode this time also, and the things that we are going to cover are we are going to discuss the use of steel deck slabs as flooring system in steel structures. Then we will discuss the introduction or some basic calculations about the dynamic wind effects as per IS 875 part 3. And then we will meet engineer Geeta from Bengaluru. So she is going to join us and she will be sharing her experiences of doing several projects in last 6 7 years, and also she will share her experiences of doing some industrial structures. So this is going to be the agenda for today, and I'll quickly start with the first point, that is the dynamic effects as per IS 875 part 3. Okay, so let me share my screen, and uh, I'll just put up. How many of you have done the calculations as per the dynamic wind effects? Yes, anyone who has done the calculations using the dynamic wind effects given in IS 875 part 3, whether it is the section 8 or section 9 or section 10 of the code. Okay, if you have not done, let us quickly discuss it today over here. So before I begin for this particular, uh, what to say, for this segment, I would whatever knowledge I have gained is mainly from professor, uh, I mean, he was earlier professor, now he's a consulting civil engineer, Professor Abhay Gupta sir. But because he is our teacher, we always call him as uh, our sir. So thanks to him for whatever knowledge I have in wind engineering, to Dr. Abhay Gupta sir. And for this segment, I also thank engineer Sandeep Dev. So he has put up some excellent videos on YouTube. So I also watch his videos and get to learn a lot of things. So I had watched a couple of his videos on dynamic wind effects, and also he had shared some Excel sheets for better understanding. So both of them, I thank both of them before starting today's segment. Okay. So when are these dynamic wind effects to be considered? So IS 875 part 3 tells us that if you're building structure to height ratio, height to minimum lateral dimension ratio is about 5. If it exceeds, it does not use the word exceeds, it says if it is about 5, that means even a 4.5 or 4.3 or 4.6, this is also about 5. Okay, so why they have used this about word? Just to leave it to the discretion of the engineer, structural engineer, to take this decision that whether even a 4.5 lateral height to lateral dimension qualifies for dynamic wind effect calculation or not. Okay, so if your height to minimum lateral dimension is this, about 5, or or the fundamental mode of vibration is less than 1 hertz. So if your fundamental mode of vibration is less than 1 hertz, that means your time period will be more than 1 second. So if either of this criteria satisfies, then your building should be checked for the dynamic wind effects. Okay, what are the dynamic wind effects that we have to consider? Let us see. So the dynamic wind effects to be considered are, yeah, I was asking who have used the dynamic wind effects in their projects. Mr. Mohammad Danish is saying he has used it in one of the RCC high-rise building that he did. 10, I don't know what 10 is. Yeah. So anyone in the audience who have used these dynamic wind effects. So Mr. Partha has used it as per the British standard. Very nice. Let us move ahead. So the dynamic wind effect, according to the code lists out four dynamic wind effects. First is the interference effect, vortex shedding, the along wind response, and the across wind response. So one by one, let us see what do they mean. Yes, Mr. Sandeep has used it. Yeah, I took your name therefore in the starting of the episode that I saw some of your videos on YouTube for dynamic wind calculations, and also the Excel sheet that you shared, that was really helpful for understanding. So these are the four effects that we should consider. What is the interference effect? So the first effect that code lists out, I think it is in section 8 of IS 875 part 3, is the interference effect. So what does it mean? That suppose this is your building. If this was an isolated building, then the behavior of this building would have been different. But let us say there is a second building in the vicinity. Then what will happen if your wind currents are flowing, and if there is a second building in the vicinity, the effect of this another building may induce some additional responses on your primary structure. Okay, to put it in other words, let us say you are going to construct a structure in the vicinity of a pre-existing structure. This is your new structure, this is your old structure. So what may happen, because of the presence of the old structure, the wind currents may undergo some interference, and the behavior of wind currents or the wind forces that this new building will uh, experience would be slightly different than what would have been if this building was a isolated standalone building. Okay, so this is what they are trying to tell you in this interference effect. So the presence of a similar structure in the vicinity may cause an enhancement of wind effect on a particular building or structure as compared to case when it was isolated or single. That's what I said. So see, the actual phenomena is too complex to calculate, or it is too complex to have any numerical mathematical expression for it. So therefore code gives you an interference factor. So you should use this factor only for preliminary design, and it should be ascertained with either doing a CFD analysis, computational fluid dynamic analysis, or you do a internal testing to ascertain the exact value of this interference effect. Obviously, this interference effect is more seen in the tall structures. Now, how to define tall structures? The definition is unclear in the code. Whatever we are discussing right now, it is with respect to the IS 875 part 3. So, how to define tall structures? That is not quite clearly mentioned in the 875 part 3. So, this is the codal provision. For low rise building, it says that suppose this is your building under consideration, this is the building you are designing, and this is a close by building. So, if the wind currents are blowing like this, and if there is an existing structure that is x distance, and x distance they write it as 5 times b. So if there is a building which is at a distance of or less than a distance of 5 times b, then you have to increase the wind interference effect, or the wind interference factor on this building has to be taken as 1.25. So that means if this building was isolated, if it was a standalone building, as compared to that, for this building now, which has another building close by, you need to increase the wind loads by this 1.25 factor. So this is what code tells you for the low rise structures. If the nearby building was more than 20 uh, times the width, if this distance is more than 20 times the width, then you need not consider any interference effect. So that is what the code tells you. Now there might be a question that, let's say, while constructing there was no building in the vicinity, but let's say after construction a new building came up to close to the existing building, then even the wind currents on the existing buildings will now undergo a change, isn't it? Suppose while constructing there was only this building and you did your building wind load calculation as a standalone building, and after a few years a new building got constructed close by. Now the wind loads or the wind currents on your building will undergo changes. So in such cases, you have to anticipate as a structural engineer possibility of future constructions, and accordingly you will have to consider the wind loads. Okay. So accordingly you will have to anticipate the possible interference. Then you have got another criteria for tall buildings given in 8.3. Here it says that if this is your building under consideration, okay, and suppose there was an existing building in the vicinity, there was this building in the vicinity, so it has given you certain zones. Okay, you can see Z2, Z3, Z4 and so on. So if this building was, let us say, A, B, C and D, suppose you have a building in this zone, suppose you have this building B. Okay, so what interference will it have on your original building O? So for that you have to check this zone. So this zone is Z4. So that means because of this building B in zone Z4, you will have to consider an interference factor of, sorry, this was Z1. It was not Z4, this was Z1. So presence of this building B in zone Z1, you will have to consider an interference factor of 1.35 on your original building. That means you have to multiply your wind loads by a factor of 1.35. Is that clear? Suppose your building was this building C. So this is in zone Z2. So presence of this building C in zone Z2 will mean that on your original building, you will have to multiply the wind loads by a factor of 1.25. And likewise for other zones also. Okay. So this is how this interference zone diagram is given to you. When do you have to consider the interference of a nearby building? When its height is equal to the height of original building is equal to the height of interfering building and up to one third of height of interfering building. If the height of interfering building is less than one third of the original height, then you do not consider any interference effect. For intermediate heights, you can interpolate this interference factors. All right. So this is how you have to consider the interference effects. So this was the first, I would say, dynamic effect given in IS 875 part 3. The next dynamic effect is given as the vortex shading. So what happens in vortex shading? Your wind currents, when they encounter a sharp, blunt object, the wind currents disperse near the edges. Now, when they disperse near the edges, these alternating vortices are formed. And because of these vortex formation, even though these individual vortexes are not large, but because it is a vortex formation in an organized pattern, it leads to the across wind force on your structure. Okay, so this also is a problem. Vortex shading might be a problem for tall slender structures. So what does your code tell you? That this is of a special significance in tall structures. Vortex shading is a special significance in tall structures, and it may lead to significant across wind responses. When will it lead to significant across wind responses? When the frequency of vortex shading matches with the fundamental natural frequency of the structure. Okay, so then there will be a situation like resonance. When the frequency of vortex shading matches the natural frequency, it will be a resonant frequency, and that will lead to significant across wind motions. Okay, if such a thing happens, code tells you to refer some specialist literature in such scenarios. This is true for very tall buildings. For if your building is very tall, what you do is that you adopt some strategies to reduce this vortex shedding. How do you do it? Either you increase the stiffness of the building, but increasing the stiffness of the building is tricky because then it will attract more earthquake forces also. And for super tall buildings, you cannot go on increasing the stiffness beyond a point. The other thing is that you can smoothen the sharp edges. So if your building plan is like this, perhaps you can make it smooth like this. Any cross section, any building cross section that resembles like this plan, where the edges they have smoothened out instead of providing sharp edges. Any tall building you can recall where they have smoothened the sharp edges. This is the plan. Yes. Anyone? So I don't know if you have seen, but if you have heard about Taipei 101, TAIEPI, in Taipei 101, the plan of the building initially was having sharp edges, but then to reduce the vortex shedding effects, they reconfigured the plan and smoothened the corners like this, concave edges like this. Okay, so this is one of the strategies to smoothen the sharp edges. The other strategy can be to have large openings in the elevation. So instead of having a straight elevation like this, you may introduce an opening like this in the elevation itself. Okay, I think there are some buildings in China, Shanghai, or I think Dubai, where they have introduced large openings in the elevation of the building to reduce the vortex shedding. The third strategy can be to vary the cross sectional area of your building. So, along the height, you don't have a uniform cross sectional area throughout the height. You try to introduce or try to vary the cross sectional areas in elevation. So, as you move up, you will see different cross sectional areas at different height. So, where do you see such a strategy being used? Having different cross sectional areas along the height of structure. So I think if you have seen about or heard about the what is that Sears Towers in Chicago, it uses this strategy, or Burj Khalifa uses this strategy. Both of them have varying cross-sectional areas along the height. So these are some of the few strategies that you can reuse in super tall structures if you want to reduce the vortex shedding. What does the code tell us? Code tells us that you calculate the frequency of vortex shedding. This is the formula, and if it matches with the fundamental structural frequency, then your structure has a tendency to undergo vortex shedding, and it may be then properly analyzed with the help of specialist literature. So how to find out this value? Let us see. So here they give a formula to calculate the frequency. Let us say, I'll just take a quick example, that your building is having a plan of 18 meters by 27 meters, and this is the wind direction. So your B is 18, your ST is a is called as the Strohal number. I don't know whether this pronunciation is correct or not, but just like you have Reynolds number in fluid dynamics, similarly this person has done a lot of work in the field of wind and fluid in general. So it is a number named after him. So for general structures, you can take this value as zero point 0.1. Let us say uh, hourly mean wind speed. Let us say the hourly mean wind speed at height was, I'm just taking some random value. Let us say it was 40 meters per second. This is after the introduction of K1, K2, K3, everything. Okay. And the width is 80. So what is the frequency you are getting, by the way? If someone can calculate. So the frequency that you get is 0.22 hertz. So time period is how much? So time period will be 4.5 seconds. That means if this structure under consideration has a time period of 4.5 seconds, then such a structure will undergo vortex shedding. Or you may say that vortex shedding then becomes important criteria to consider. Are you getting this? So generally you will see that the normal height buildings will not have this kind of a time period. Yes or no? Your normal G plus 15, G plus 20, even G plus 25 structures will not have this kind of a time period. This type of a time period will be there for, let's say, G plus 30, 35, 40 onwards. Okay. Otherwise, you won't get this kind of a time period for your general buildings. So what I'm trying to tell you, that for your general height structures, vortex shading is not a problem. So you may not be very worried about it. Okay. So this was the third interference. This was the third dynamic effect. No, sorry, this was the second dynamic effect. The third is the along wind response. Along wind response means this is your plan of the building, and wind is hitting from this direction. So the dynamic amplification of wind loads in this direction is called as the along wind response. So how do we calculate it? We calculate it by a method called as the gust factor method. It is basically a pseudo-dynamic method because we do not calculate the wind forces on the basis of the modal behavior of the structure. We just do it on the basis of a factor, and that factor we multiply by the static wind to get the dynamic wind effect. So basically we take the dynamic wind equal to G times the static wind. So it is similar to, you may say, the equivalent static method, where we are not doing the actual modal analysis, we are just enhancing the value by a factor. So that is similar to what we are doing over here. We have a static wind, we multiply it by the gust factor to get the dynamic wind response. So therefore we are calling it as the pseudo dynamic method. Okay. This method, or this type of mathematical expression, was first given by a person called as Davenport in the year 1967. I don't recall his first name, but he did a lot of work in wind engineering, and it is his method that in all the international codes we today use as the gust factor method. So the gust factor depends on the wind characteristics, height of the structure, dynamic properties, time period, damping, terrain category, etc., etc. So there is a long calculation procedure given to you in the code. So I've taken the screenshots on the code itself. Here this is phi. This is not G. There's an amendment to this clause. It is G. Sorry, it is phi over here. So this is given as the gust factor. Out of this term is the base component of your wind currents, and this is the variable component of your wind currents. So you take both into account to calculate this gust factor. And there are a lot of calculations given to you. It is a step by step algorithmic approach that you have to follow, and you get this gust factor. Once you get this gust factor, you can multiply the wind pressure by this wind coefficient CF. This is given in table number 21 of IS 875 part 3, and you multiply it by the, so just like you have the external and internal pressure coefficient CP, CPI, you have this force coefficients for rectangular buildings. It is given in table 21 if I remember correctly. So this coefficient into area into pressure. So this is the static wind speed. You multiply it by G to get the dynamic wind effect. Okay. And then you can get the overturning moments at the base, or you can get the total deflection at the top. All those values you can get once you have these forces, dynamic forces. So gust factor is calculated, and there are a lot of formulae. It's a formula intensive work, so it is better to prepare some Excel sheet to automate this calculation, because every time you can't calculate this. So the formula goes on, and you calculate the gust factor. And then you can also calculate the peak acceleration. This peak acceleration generally is required for the human comfort. So for that, sometimes you may need to calculate this peak acceleration. So all these things can be easily done, And the fourth response is the across wind response. That means wind is blowing in this direction, but the response is happening in the perpendicular direction. Okay. Mr. Rahul is saying table 21 is for the combined roof system. Oh, no, no. Then, wait. Which is that table for rectangular buildings? I'll just search. CF table. Ah, this is figure 4, not table. Figure 4, page 35. Figure number 4, page 35. Okay. Yeah, that is the table. All right. So across wind response, again, your code tells you that across wind response due to vortex shedding is significant. Just a minute. Yeah, it is significant for tall, slender structures. For general structures, that means if it's a not a tall structure, mid-height structure, you may ignore it because it is not significant. The calculation for across wind response is given in the code section 10.3. So in this case, it is a slightly different approach. First, you calculate the peak base bending moment. This is just like the total overturning moment in case of earthquake. And this you calculate first. Once you have this value, of course, all these independent terms are given to you in the code how to calculate them. Once you have this overturning moment at the base, then you can calculate the distribution of these forces at every level. Okay, so this is slightly different way of calculating for the across wind response, and you can work out the peak acceleration also if you want to calculate. There is one term, this CFS term that you see over here. So this CFS term you can calculate given the curves in figure 10 and 11. So these figures 10 and 11 give you the calculation or the way to find out this CFS. Okay, so this is how you do the dynamic calculations. Now what I have done is that if I wanted to discuss this using a sample model, Mr. Sandeep is saying, how can we use this method when the structure is not rectangular or square as the charts for CF is? Yeah, correct. So you can see this CF chart are only given for square and rectangular structures. In rectangular also they have given it only for an aspect ratio of 1 is to 2. Okay, or 2 is to 1. So other than that, any other randomly shaped structure, you don't have the methods and ways to calculate CFS. So I don't know, then you may have to go for some wind tunnel testing, or I'm not quite sure how you do it because code does not tell you anything about it. Okay, it just says CFS is the across wind force spectrum coefficient. So for a non-rectangular, non-square building, what to do? I don't know. Mr. Sandeep is saying, do we need to assume the structure as equivalent to rectangle? No, but then the behavior entirely changes in case of wind. Suppose your structure was this shape, triangular in plan, and you assume some equivalent square. Then the behavior of this square will be totally different to that of this triangle. So I won't suggest assuming some equivalent squares or rectangles. I would suggest you to then go for some wind tunnel testing or do some CFD testing. CFD analysis, computational fluid dynamic analysis. Okay. Yes. So what we will do is to quickly understand this in a better way. I'll just share my screen, and what I have done is we will quickly see an ETABS model, and then we will try to understand that if I had to calculate the dynamic wind effects for it, what would happen. Okay, so this is a sample ETABS model that we have prepared. It's a plan, it's a rectangular plan building. I hope you are able to see this. It's a rectangular plan building having 18 meters by 27 meter plan size. and its height we have given as 96 meters. Okay, so the topmost story, you can see story number 24 is having a height of 96 meters. So this means it qualifies for the dynamic wind effects because the height to lateral dimension exceeds 5. So this structure qualifies for the dynamic wind effects. Now what we will do is that to understand how the dynamic wind effects will be calculated, I will mainly focus on the along wind and across wind responses, because interference anyway, we cannot predict interference. So the code tells you that only take a preliminary value for interference. If there are a lot of other structures in the vicinity, code always recommends you to go for a CFD or a wind tunnel testing. So interference I am not doing. Vortex shading probably we can do, and we can do the along wind and across wind. Okay. So let me share. How do I share? Yeah. Let me take you to our Excel sheet, and in making this Excel sheet, I had asked for some help from Mr. Sandeep Dev. So, yeah. So, this is an Excel sheet that we have tried to make. So, it will calculate the along wind response, and it will also calculate the across wind response. So, you have to input the height of the width of the building. Right now, this is my building. This is 18. This is 27. And I am considering wind in this direction. Okay. So, this will become the width. So width of the building is 18, height is 96 meters. We are doing a very quick calculation just to see what sort of values we get. This is the level under consideration, S equal to 0, because I want to take the overturning moments and tip deflection. So I will have to put the value of S as 0. Then width is this. Terrain category, let's say uh, we are in a city center, highly densely constructed city center. So terrain category is 4. Let us say we are in somewhere in Bangalore or Hyderabad. So basic wind speed is I think 33 over there. So let us take that. K1 is 1.05. K2 will be calculated as per height of 96 meters. So K2 is being self-calculated. This roughness factor is 2 times the turbulence intensity. So turbulence intensity is given over here. It is given in section 6.5 of the IS 875 part 3. This is the peak factor for upwind velocity fluctuation, GV. All these terms are properly defined in the code, okay, along with response. So I'm not going over there. You have to put the fundamental natural frequency in the along wind direction. So that means in this case, I will have to put the frequency in the X direction. So I will have to go to ETABS and I will have to check the modal frequency. So in this case, I'm not sharing the screen, but in this case, the modal frequency comes out to be 3 point. How much it is coming? It comes out to be 3.27 seconds. Okay, substantial frequency 3.27 seconds is the modal frequency in the fundamental mode, 3.17 seconds. So I will put a 3.17 value. So frequency will be, sorry, time period comes out to be 3.17 seconds. Frequency will be 1 upon that. So I put that value. Then accordingly it calculates, and the gust factor comes out to 3.77. What does this gust factor of 3.77 mean? That all the static wind responses that we had calculated, all the static wind response that we have calculated needs to be multiplied by this gust factor. So that means our wind in dynamic is getting amplified by this 3.77 times. Is this clear? Hello? I think it is clear. Yeah. So this is how this gust factor calculation has to be done. Now suppose at some reference height you wanted to calculate what is the total UDL acting at a particular floor level. Then you can put this reference height, and you can put this CF factor from figure 4 as we had just seen. So from this figure 4 you put this CF factor, and then it will give you the wind load per unit height, okay, at a particular reference level. So at 4 meter, this is by 116 kilonewton per meter height, sorry, kilonewton per meter wind force. How can I convert it into force value? So I just multiply by the half of the floor distance above, half of the floor distance below. Right now our floor to floor heights are 4 meters, so I can multiply it by 4 meters to get a value in kilonewton units. This value will be the total wind load acting at a particular floor level. Okay. So in this way, you can use uh, this Excel sheet to calculate the wind loads at different floor levels. Mr. Akash is saying, have you applied stiffness modifiers for this model? No, not as of now. Not as of now. I have not used the provisions of 16700 for this case at least. Yeah, you may ask then why still the time period is coming out to be 3.17, right? Because the columns were very far spaced. Therefore, the system is becoming quite flexible right now. Okay. So this is how the along wind response has to be calculated. And then similarly, you can calculate the across wind response. In this case, you have to first put in the time period in the perpendicular direction over here. So if I was considering the response in wind in this direction, I will have to put the time period in the perpendicular direction and 1 upon it because I want to calculate the frequency. So in this case, in the other direction, the time period was, I'm not showing you on the screens, but the time period was 2.95. No, sorry. It was 2.95 over here. In the x direction, it was 2.95. In the y direction, it is 3.17. Yeah. So you can get the across wind responses also. Again, for a reference level Z, you can calculate the across wind responses. Initially, you will see that at lower heights, you will see the across wind response was 4.82. Compare it with the along wind response, which was 114. But as you increase the heights reference level, suppose I do it at 40 meters, then you will see substantial increase in the uh, across wind responses also. Okay. So if I was at reference height of 40 meters, you will notice that the along wind response is 191 kilonewton per meter, across wind response is 48. So now it has started becoming substantial. Suppose I was at 72-meter reference height. My total structure height is 96. This is the reference height. So now it has started becoming substantial. So for tall structures, across wind response is substantial. Otherwise, for shorter structures, you may ignore the across wind response. Good. So this is, I think, what I had to tell you for this. Uh, this is what I had to tell you about the dynamic wind effects and their calculations for taller structures as per IS 875 part 3. So now if you have any questions, we may take, or otherwise I will go to the second segment where I want to discuss a few things about the deck slabs. Okay. Yes, any questions or I should move? Okay, so then I move ahead and I'll take another discussion point. So the next topic for today's discussion is about the deck slabs. So use of deck slabs as flooring system in steel structures. Now generally in steel buildings, what is the flooring that we use? So either we use checkered plates or we use gratings. Okay, I think you must have seen these two commonly used floor systems. So there is a third floor system also that we may use in steel structures, and that is the deck slab with concrete topping. So it is nothing but a steel plate. You can see a corrugated, embossed steel deck plate. It is resting on your steel beam. These are shear studs to connect this deck sheet with your eye section, and then you put concrete on top of this deck sheet with a minimum reinforcement. So this is called as a deck sheet flooring system. How many of you have used this type of a deck sheet flooring system in any of your projects? Yes, anyone who has used deck sheets in their deck sheet flooring in their projects? Hello. Okay. So if you have not used, it's easy thing. I think it's easy to use deck sheets. So we'll just quickly discuss. So steel deck sheets are nothing but they are deck sheets cold formed into corrugated profile sheets, and these steel sheets are typically 0.8 mm to 1.2 mm thickness. And the advantage of using a steel deck slab, that you may use the steel deck sheet as a shuttering during the construction stage. So that means you don't have to use all props and centering and all those things that may not be required. Your steel deck sheet itself acts as the shuttering, and then as a reinforcement after concreting. So initially it is acting as a shuttering. You need not put any props. You just ensure that it is resting on beams. Okay. And once this is done, once you do the concreting, then it starts acting as a reinforcement also in the post construction stage. So if it acts as reinforcement in the post construction stage, then it is called as that this is acting as a composite slab. Okay. So some steel deck profiles you may use only as shuttering. Some other steel deck profiles you may use as shuttering plus as composite slabs both. It depends on the profile of your deck sheet. There are different manufacturers that make these deck sheets. Some of them I have named over here. These are the typical profiles that you get in deck sheet. You can see the profile. There are corrugations, there are embossments. These are the ribs that you create. Okay, these are the depths. So this is a 46 mm depth. These are the corrugation widths and all these things. This is a larger depth, 51 mm depth. This is having a 60 mm depth. This is having an 80 mm depth. So different profiles are used for different purposes. This type of profile is only used as a shuttering. This is used for shuttering plus as a composite slab. This is also used as shuttering plus composite slab, shuttering plus composite slab. Okay. The first profile is only used as shuttering, else other three can be used for composite action as well. These are, I mean, these images I have taken from one particular manufacturer, but almost all the manufacturers make the similar specification deck sheet. Okay. So what are the challenges in design? The challenges in design are that in the construction stage it is easy, because in the construction stage, as I told you, it acts as a shuttering. So you have to check the thickness of the deck sheet, and you have to check the bending moment carrying capacity of this deck sheet alone. Okay. For bending, for flexure, and for shear requirements. And you also have to check the deflection of this independent deck sheet without concrete under the construction loads, and you also have to check its fire resistance. So this part is easy. The difficulty is when you are going to use this deck sheet in the composite action. That means after you put concrete, this is also going to act as a reinforcement. So then in that case there is challenge, because now you need to check this for the composite behavior. And the challenge is that, let's say I am showing an elevation. This was my concrete and this is my steel deck sheet. Now, for these to perform together, when they undergo bending, the in plane shear that is generated, the longitudinal shear that is generated, your deck sheet and concrete bond should be able to take that longitudinal shear. If it is not able to take this longitudinal shear, then there is a slippage that happens between the concrete and steel deck. And if slippage happens, then it does not act as a composite behavior. I mean, it will not show a composite behavior. So the longitudinal shear, or what is called as the in-plane shear action between concrete and steel, needs to be ascertained, and that is the biggest challenge in the design of deck sheets. So this is what I was telling you, that suppose this part is your concrete, this part is steel deck. If it behaves as a composite, then it will behave like this, correct? But if it is not behaving as a composite, then it will have its individual neutral axis, and then they don't behave as a unit. So your composite action is lost. So the calculation for this in-plane shear action, in order to ascertain whether this is behaving as a composite or not, is numerically quite challenging. Okay, it is numerically quite challenging, and therefore you are not able to do it by a numerical formulae. Why is it numerically challenging? Because a deck sheet has these crests and troughs which adds to the bond between concrete and steel. It has these embossments, it has ribs, it has shear studs. There are a lot of elements which make it difficult for the numerical calculation. So therefore, either you do some actual testing, you do a push test to ascertain the in-plane shear characteristics, or you try to do a FE modeling. So these days, using softwares like ANSYS or Abacus, you can do this type of FE modeling also. But generally, for practicing engineers, there is an absence of this data, so we are unable to calculate this composite action. So in that case, what is given? What is the solution? The solution is that the deck sheet manufacturers, they either give some ready to use design tables. So as a designer, you just have to refer that table and you choose the profile as per the load, as per the span, and as per the fire resistance. Or some of the leading deck manufacturers also have developed their own small software, small softwares which you can use as a designer to finalize the standard profiles. Okay, anyone who has used these types of tables or profiles or these softwares to finalize the deck sheets? Anyone? No one. Very good. So I'll just show you a sample of these easy to use software, and I will also show you a sample of this type of a table. Okay. So let me share my screen, and what I will do is I'll share a table. Mr. PD Vlog has referred some tables. Where is the table? Wait. Let me just, yeah, this is the table. So I'll be taking one manufacturer. Uh, just wait a minute. Mr. Sandeep is saying that he learned while doing one of the courses. Mr. PD Vlog has used it before. Very good. Just a minute. Somehow I'm not able to see the. This is, yeah. Okay. So this is a table, a manual that is released by Tata Comfloor. So Tata in UK, United Kingdom, they have brought this company. They have brought out this company Comfloor. This Comfloor was a market leader in deck sheet manufacturing, and so Tata has just brought this company, and now this is marketed as Tata Comfloor. Okay, in India they have this Tata Blue Scope. So in India, deck sheets are manufactured under the name of Tata Blue Scope. Okay, so you can use these ready to use tables just to finalize the uh, type of deck sheet that you would want to use. I'll just give a sample. We'll go with this Comfloor 60. Okay, how to use this table. So we will refer this, and let us say we are right now. Wait a minute. Arre, there is this problem with this. I don't know. Yeah. So we will take this continuous spanning right now. I am not able to write over here, right? Okay. Is this the way to write? Anyway. So this is the sample given to you. It's a double slab. I can write. Yeah. It's a double continuous slab deck sheet arrangement. This is the total load applied. Okay. It is a Comfloor 60 profile, standard profile. Okay. This is the fire resistance to be considered. This is the total slab depth. And then these are the thicknesses. Now, how to use this table? Suppose the total load that you need to resist is, let's say, 7.5 kilonewton per meter square. This includes all the live load, all the dead load, everything. Then how to look at this table? Suppose you are looking at a 130 total slab. That means 60 is the profile, and you will have a 130 total concrete. This will be 70 because 60 is the profile. So if you have such a scenario, then if you want to resist 7.5 kilonewton per square meter, you will have to provide a beam to beam span of 3.9 meters. Is it understood? Hello. Is it clear how to look at this table? So these values that are given to you are the values for the secondary beam to beam span. Or suppose I wanted to resist 10 kilonewton per meter square total load, dead load plus live load plus finished loads, then I have to maintain 3.51 meters center to center span. Is it clear? This value in the bracket is the value for the wire mesh or the reinforcement that you have to provide at top. This is the secondary reinforcement to arrest the shrinkage. All right. So this is the nomenclature given in the brackets. Suppose, and yes, it is a 1 mm thick deck sheet, Comfloor 60, and this will be okay to take a load of, let's say, 7.5 kilonewton per square meter if your secondary beams are placed 3.9 meters center to center. All right. This is the way to use this table. Okay. So either you use this table because you are not able to do the design, or then there are software given by the manufacturer. So you can use these. Uh, you can use those standard softwares that is given by the manufacturer. PD blog is asking, this loading is excluding self weight on RCC load. Am I correct? No, no, it's inclusive of everything. It is inclusive of everything. Yeah. Okay, I'll just show you a small software that these companies present, and it is easily available on their websites also. Can you see this? So this is a software of the same manufacturer for which we were seeing that standard table. Okay, so it is the same company, Tata Comfloor. It is their own developed software. So you just got to put, now see, the problem is that you only can put their standard profiles. You cannot create any random profile that you want. You can only put their products. You can put the thickness that they have. Grade is 350 grade. Whatever span arrangement it is for you, you put whatever is the center to center beam spans, you put the concrete grade, everything you have to put over here. Density of concrete, let's say it is 2500. Okay, and you put everything. Then you go to loading. You have to define the loads. All right, you have to define the loads, and then you click on design, and then you can click design. And in this way the design happens, and then it tells you all these things. Can you see? So right now what may be happening, that in the construction stage it is okay, 0.78 is the utilization ratio, 0.92 is the utilization ratio in the composite stage. In fire it is a problem, so this may not be able to resist the fire, so we may have to go back and change the reinforcement to enhance its fire resistance. Do you get it? So if I change the reinforcement, and now it becomes safe in fire also. Is this clear to everyone? So when I put more reinforcement, the fire resistance improved, and it got safe in fire also. So these are some small softwares that the leading deck sheet manufacturers have. So either you can use the tables, or you can use these softwares. Okay, these softwares are easily downloadable, you can download it from there, and these are all the checks. And suppose you want to get a detailed PDF, you can use this print button. So this is what I had to tell you about this deck sheets and use of deck sheets in composite slabs. So if there are any questions, you may ask, or we go to our third segment. Okay, so I'll go to the third segment now, and questions, if there are any, you can type in, and we would take them as and when we get time. So we move on to our next segment, which is the experience sharing. And in this segment, we always invite young engineers to share their experiences, and we try to learn from their experiences of doing projects. So for this episode, we have engineer Geeta with us. She is joining us live from Bengaluru. So she has done her engineering and masters in structural engineering, MTech in structures, that is, and she has been working as a structural engineer at Amin Bhavi and Hegde Consulting Engineers, Bengaluru, and their firm is involved in design of industrial, commercial, and residential steel and RCC structures both. And before this company, she worked for a different organization. She has a long experience, and she has an experience of doing several projects, close to 40 plus projects in her career till now. So we are very happy to welcome her. So let me see. Oh, perhaps she is on mute right now. Oh, yes, here she is. Hello, Geeta, welcome.
Hello, sir. Hello, everyone.
You need to talk a little bit louder.
Yeah, sure, sir.
Sorry to keep you waiting for so long. Our
Yeah.
other sessions went a little more than expected. Sorry
No,
for
it
that.
was night session, like nice session, sir.
Yeah. So thank you for
Even
taking
I
out time.
enjoyed it a lot. Yeah.
Acha, thank you.
Thank you, sir.
So thank you for taking out time and joining us today on this episode.
Thank
So
you, sir.
we had invited you to understand and learn from your experiences, and you have a large work experience behind you. You have done several projects in both the organizations that you have worked for. So if you would like to tell us about it.
Yeah, sure, sir.
Yes, you may first tell a few things about yourself, and then
Yeah.
maybe some projects that you are doing, and few interesting industrial structures that you have done that we would like to know from you.
Yeah, sure, sir.
Yes, over to you. So audience who want to ask questions to Geeta, they may chat. I mean, they may put their questions in the chat box. We will take them up.
Sir, I guess like you all can see the slide.
Yeah, we can see them.
Yeah. Uh, I have done my master's from SMVITM Bantakal in the year 2013 to 17, and MTech from MIT Manipal in 2017 to 19. And soon after that, I started my career from in Simons and Associate. It is an architectural firm, and then recently I joined Amin Bave and Hegde Consulting Private Limited in Bangalore, and their main branch is in Dharwad. And I want to tell you about like the past work that I have handled when I was working in a Simons and Associate. There are several projects that is from in residential, commercial, office building, school building, auditorium, apartments, beach resorts. Those are the kinds of the project that like I handled in Simons and Associate, and even in a freelance project I handled the similar kind of projects, and nearly about 40 plus projects that I've handled in both in office as well as a freelance consultant. And the initial days when I joined the architectural firm, I faced lots of a problem, like it was very difficult
Your
to
first
understand their.
your first firm was architectural company or it was a structural
Yeah,
consulting?
architectural company, sir.
So your boss was an architect,
Yeah, he was an architect.
and you were working as a
And
structural engineer over there.
yeah, and
Okay.
only two were there, so senior and me.
Okay.
So it was even difficult for him to check all the drawings that I've done and whatever the analysis that I've done.
Yeah.
So all the burden was on me, like you have
Okay.
to take the project independently like that.
Yeah.
So when the plan is given like from the architect, then I had to make the structurally like suitable, and I have to put the column marking and all, and column position and all, and then I have to discuss with the architect. When sometimes like he will ready with whatever the columns that I put, and sometimes he will like, no, this is the area that you have to avoid the column and you have to avoid the beam, like that
Yeah.
was there. And simultaneously like I had to study the analysis, like how it as will do, and even I had to check the design, and even the detailing I had to refer to the SP34 and all, just to deliver it to the drafting persons. And I had to coordinate with the architects, draftsmen, site engineers, and even the clients.
Okay.
So and even convincing the whatever like structural requirement is there to the architects and even the client is was very difficult for me in the beginning. And even it is like something surprise will come from the structure like architect, like after doing like after raising the footing and even after the construction of the footing at the site, they will tell like when it is a commercial building, they will tell like, no, we don't want to give it to shop, and we want to do it a gym, like that it was
Yeah.
coming. And
Yeah.
sometimes what happens is like in the second floor, they will add the extra floors. So in the beginning, I was not familiar with that. Like whatever the drawing is given, I used to do it, and then after some experience, and
Yeah.
then I started taking the additional load and even the additional floors for the
Yeah.
footing design. Yeah. And sometimes it is like they used to remove the wall, and it is like then they will come to us and then they will start arguing like, no, you have given the column in the between, like that. So it was very difficult, and like even architect sometimes he will convince, okay, no, it is our mistake, but the
No.
client is like, no, I told you in the beginning itself, like that they will tell. So it was very difficult, and I had to check all the like drafting also I have to check, and then when it goes to site, there also I had to go to site and I have to check whether it is as per the drawings or not.
Yeah.
That I had, and even till like the end stage, I had to involve in the project. So it is
No.
not like I list the drawings and then I just started working in other projects. But it was like simultaneously I had to take other projects too.
Yeah.
Uh, it was
So you
like
had to do several projects at once.
yeah, sometimes it is like in a day I'll be handling 10 projects like that.
Oh, is it?
So yeah. And it
yeah,
is like architectural commitment will be there, no, like they will tell the
yeah,
client, no, I'll give the details, everything in 2 days, like that.
yeah, yeah.
So yeah,
And lot
and
of
these are,
coordination, lot of
yes sir,
coordination with these services also, right? Lot of
yes
coordination
sir,
with
yes
services.
sir, that too. Like we had to take this pipelines, and for that we had to give some provisions, like that.
Yeah, yeah, yeah,
So we we were in all the stages. So if something like changes will happen, when we don't know what changes had happened, then it was very difficult when we visit the site. They will just put all the blames to us, like that.
yeah. Life is tough
Yeah,
for
and
structural engineers.
huh?
Life is
Yes,
tough
sir.
for structural engineers.
Yeah. And even when it is and even we should design the economical projects. Like it is not
Yeah.
like we are giving heavy detailing, and they
Uh,
will not like listen. Even the
uh,
client is like, no, your this bars sizes are all coming heavy, and you are doing the heavy like detailing and all.
uh.
So even we had to take that also. Like in the private, this is the problem we all face. Like,
Yeah,
and I want to show some of the projects that is completed.
yeah.
And yeah, this is the beach resort that I've done, and now this inauguration is also done. Uh, this is the completed stage, and
Yeah.
this is the residence, that is like whatever it is in left, that is 3D elevation and 3D view, and similarly they have done at the side. These all the details, no, like the projection, and how it should become, it should come, that all we had to sit with the draftsmen and even the
Uh,
architect sometime, and we had to discuss like, okay, this it is coming at the upper level, and we have
uh,
to give the projection, like that.
yeah, correct. So you can do this rendering also yourself?
No sir.
Acha.
Yeah,
Okay.
only the structural part I was handling, and this detailing. Yeah,
Yes.
and this is the office complex that is my office, and this is a school project. I have done it as a freelancer. Um,
Acha.
and this is a commercial plus building project. Here, just after the commercial, there was a problem, like uh, the plan, sudden change in the plan. We had to eliminate the columns at the commercial complex, because they don't want the columns in between. They wanted the free space. So I gone for stub columns, and even the apartment, the whatever the waters from the toilets and all, we had to take it from the trench, like hence we given the flat like folded kind of slab,
Hmm.
so that all goes to like all the pipes will be in that folded sunken portion, and it is
Uh,
taken at the corridor, and it is taken out, like that.
so the downtake pipes, you could not take them through the commercial space. So you had
Yeah,
to have a sunk, and
yes sir.
all the pipeline service lines were taken through those sunks into the corridors.
Yes, sir. And it is
Okay.
like if we give anything at the commercial complex, no, if any leakage is there, and if
Yeah.
something happens, then it is like the
Ah,
this
okay.
shop can't be sold. So,
Yeah, yeah, yeah,
so we had to take care of that.
yeah.
So this is just a 3D elevation I have, and this is the auditorium that I've done. Um, and even this is a residence, and this is a finished auditorium that recently they completed. This is the
This is as a
project that I
freelance.
have.
As a
No, no,
freelance.
no, yeah, no, 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 this is all from the office. The
Office.
freelance I had, yeah, I have shortage of this thing, like photos,
Okay. Okay.
yeah. And this is the apartment project that I was handling, and now it is in like first floor level. So all the drawings are ready, so it is going to site, and the construction is on process.
Ah,
And this is the freelance project that I've given, but it's still in this thing.
Under
plinth
construction.
level, yeah, under
Okay.
construction. So car
Okay.
parking is coming over there, and after that, the G plus 4 building.
Okay.
This is in Bangalore. Yeah,
All these
and
projects were in and around Karnataka.
yeah, yes, sir.
Okay. Yes.
The present projects that I'm like doing in Aminbabi and Hegde, they have both RCC as well as the steel structure exposed
Now
here.
this is your present company that you are talking
Yeah,
about.
yes,
Okay.
present
Okay.
company. Yeah,
Okay. Yes.
and here, like in the month of December, at the end of the December, I joined here,
Please, please
and
please tell a few things about the company first before proceeding. Just basic
yeah.
intro.
Yes, sir. Amin Pavi and Hegde, it is actually a Dharwad-based company. They have their projects all over India and as well as some part of Africa and all. And they do this industrial sugar factory projects and
Hmm.
water board or something like that kind of projects. And they have separate design teams. And it is like they are assigned for RCC, someone like that, and this one they also take government projects and even this thing what it is educational institutional projects and all,
Okay.
and they have exposure in all the fields,
Hmm.
like residential, canal, and even the industrial, uh,
Hmm.
like that, and educational buildings and
Hmm.
universities, like those all the projects.
Yeah.
And the software they were using is the STAD Pro here, and even Design Excel.
Hmm.
And first, when I joined here, I was assigned with the industrial structure, that is around 2 floors. It was a RCC, and after that, it is a steel structure, and
Okay.
even a shed, workshop building I have assigned with,
Hmm.
and some of the RCC building I had taken, that is around G plus 4, like that. And currently now I'm working in a my one project here. The software I'm using is the ATAPS and Safe, and even I'm handling industrial building also, that is around the 22.5-meter height. Uh,
Okay.
and industrial projects that codes followed are IS 456 RCC Part 1. Sorry, Part RCC. For the RCC part, we follow IS 456 and IS 13920. And and other for the wind load and dynamic, uh, earthquake load, that we follow IS 1893 and IS 875 Part 3, and IS 800 for the steel design. Here we follow the working stress method because we use ISMB sections here, not this built up sections, the plate girders and all.
Okay.
And in the industrial projects, the understanding the GA drawing is must, because in a different portion, a different platform will be having the equipment position, like equipment will be there. So we have to, before drawing the deciding the beam and all, we have to study the GA drawing first, and even the elevation and all we have to study, because like we have to transfer all the loads, and there will be some equipment that is starting from the ground, and it will be at till the 22.5-meter level, the silos will come. So we have to give the cutout, and we have to study like at what level the loads are transferred. So bolt positions are there that we have to study, and after that we'll be deciding the beam, like whether this much beam is required or that, or like that, before modeling it in a stat. And then the dead load, live load, and equipment load which is given from the supplier, that we have to take, and that we have to put in a beam, like where it is coming, like a point load or the UDL. It depends on the load. And then wind loads and seismic load is assigned as per code, and designing is done as per IS codes, and then the connection design we do. And PB shared that the codes allowed are ISA. This for the wind load I have taken IS 875 Part 3,
These types
and
of projects also you handle? These types of
yes,
projects also you handle?
yes,
Okay.
Yeah, first
PV sheds
one of
and
this, yeah, first one of the shed I have done as per limit state, and
okay,
one more project I have done that is a steel shed, so like ISMB sections, ISMC section that we gone for. That I
okay,
have done as per working stress methods.
okay.
And you can learn so many things in a consultancy firm. If it's an architectural dominating company, then you will be updated with so many challenging projects.
Yeah,
That is like yeah, different. It is a like they will come up with different ideas. So you have to like you will get lots of things to learn,
yeah,
and which will help you doing the freelance project actually. And structural consulting company, you can learn from seniors, and even you will get lots of knowledge from them, and even you will get strong in your basics. And this will depend exactly, it will depends on your company atmosphere.
yeah.
um, and I was I was interested in a consulting firm, not in the MNCs, because
Uh,
I feel like it is they will assign some task, and you should keep on doing it, and
you're
it
talking about
will take
large.
time.
Talking about large consultancy firms,
Yeah,
big
large companies. Yeah,
international
yes,
companies versus
international
working
companies.
in a smaller company.
Yeah, and
Okay.
there you will be used to yeah, like American code or European code like that. So it
Uh,
is very difficult for you to come back to the Indian code, and the site exposure you will not get from the large companies.
uh,
So I was interested in local the consultancy, small or medium, like medium consultancy firm. So,
uh. So
yeah,
according to you,
then
medium consultancy firm give you more exposure as a structural engineer to work.
yes, sir. So
Okay.
even like you can learn in a big consultancy firm, like the large structure, large high-rise buildings and all you will get. But the thing is, when you want to handle like the surrounding structures, or you want to gain the knowledge, then it is like uh, better to choose the small or mid consultancy firm.
Yeah, true. So in
This,
larger companies, it becomes very super specialized work that you have to do day in, day out.
yeah,
Uh, yeah,
yes, sir.
true. Mr. Sandeep is saying, but pay scale is also important. They earn in dollar, then pay us high. So he's saying large companies will pay you well.
Yeah, but the it depends on you. Like if you want to depend on their like the salary, then it is okay.
Yeah. So you are saying you like working in slightly smaller or medium level consultancy firm
Yeah,
because because
like
that
as
way you are also able to take the ownership of entire project, which is not
yeah,
possible in bigger companies.
yes, sir. And it is
Yeah.
like in after like 5 years or like that, you can join the MNC, and because you will have all the knowledge, no? Like
Yeah.
even what these people are doing as well as what they are doing, like that.
Yes. Okay. Interesting. Anything else you want to tell us? So between working stress and limit state, which method you found leads to efficient design, more economical designs?
Economical is a limit state design. Even the weight comes very less. But this, if you are going for ISMB sections and all, the total weight, like whatever we are steel ton we are getting, no, that will come high. So, but for the industrial structure, like they are going for the higher safety, so they'll
Uh,
not go for the local failures and all. So this they will restrict to the uh, working stress method.
Working stress. Okay.
Yeah,
No risk. They don't want any risk or any case of any local buckling failures or
yeah,
local compression failures. So they are going for hot roll.
yeah.
Okay. And you use tubular sections in your projects?
What's that?
Tubular, hollow sections.
Hollow section? No, till now I didn't use it, but they are doing it.
Okay. Very nice. Anything else you want to tell us? Any message to the audience that you want to give?
Uh,
So, if there are any questions you want to ask, or if there are any questions to Geeta, you may ask her. Or if there are any questions on the previous two segments that we took, you may ask now by typing in the chat box. Mr. Sandeep is saying, but IS 800 2007 LSM costs high. That is his guess. So, what did you find from your own experience of working? So, LSM
uh,
design is more efficient and economical
yes, it is economical compared to working this thing.
compared to working stress.
Yes,
Okay. So, in your industrial structure, generally it is a mix. I mean, it is a RCC plus steel that you have to do.
yes,
Okay. What about the foundation systems that you follow?
like it is isolated footing
Okay.
like that. Depends on what load and the spacing.
Okay. And till now, you have been involved in doing any international project as well, or are you doing Indian projects?
Indian.
Okay. So you have followed the Indian standards till now.
Yes, sir.
Okay. Good. Thank you so much for sharing your experiences, and thank you for taking out time and joining us today on this episode. So, yeah, thank you.
Thank you, sir.
Thank
Sir,
you.
and he asked one question, no? Even I wanted to know, like, what you feel, sir? Like, it is a working stress method cost more or this thing?
But it was asked to you, na?
Yeah, but still, because recently I started taking the project in this
Okay.
thing, steel structure. So,
So working stress, no, I'll tell you, LSM costs will be high when you are using members which are not suitable to take compression, and when you are using members which are not suitable to act as flexural members. Okay. So for example, if you are using very thin webs, or if you are using sections which have very thin flanges, then when you do it by LSM, it will cost you more because LSM pays high penalty on the designer uh, who are trying to use these types of sections. But when you are using sections which are, let's say, inherently strong in the local failure, that means section like hollow sections or sections like hot rolled sections, then the LSM will cost you less. I mean, using the LSM will cost you less. So basically, LSM is a more rational approach which penalizes the sections which are unsuitable and which sort of promotes the sections that are structurally stable and efficient. So it will depend on the type of structures you are choosing, which decides whether doing it by LSM will cost you more or high. So single line answer would be if you are using tubular sections and if you try to do it by LSM, it will cost you less. And if you do the same design by WSM, when I say WSM, I am saying the WSM of 1984. Okay, because 2007 also has a WSM in section 11. So I'm not talking about that WSM. When I'm saying WSM, I'm saying of talking of WSM 84. You are also using the 84 code, right?
yes, sir.
Yeah. So I'm comparing that WSM with IS 800 2007 right now. So if you are using tubular sections or hot rolled sections, doing it by the LSM will be more economical. But if you are using sections like angles or channels which are not very good for flexural compression members, then doing it by LSM will cost you more. So LSM is sort of penalizing the unsuitable sections and it is awarding the suitable sections. Yeah. Mr. Sandeep is saying most of the Indian authorities are not accepting LSM yet in heavy industry. No, I don't think so because most of the companies that I have seen in heavy industry also they accept the LSM. Yeah. Mr. Sandeep is saying Geeta is my classmate during four structures we are pursuing. Yeah, you are right. Yeah. Yes. Anything else? Any other question to Geeta or to me for the past two segments that we discussed? Okay. So I think then that's it for today. Today we discussed about the wind load calculations for dynamic effects. Then we discussed a few things about the use of steel deck for flooring systems. And then we had a conversation with Geeta where she shared her experiences of working in consultancy firms and doing several projects over her career. So that is all what we have today. Thank you, Geeta, for joining us
Thank you,
and
sir.
best wishes for the work you are doing. Thank you.
Thank you, sir. Thank you.
So that's it then. Thank you. And thank you to all our audience. This is all we have for this episode. And now it's goodbye. We will see you in the next episode with some more problems, with some more ideas to discuss, and with new people to meet and to learn from their experiences. Thank you. Bye bye. Have a good weekend and be happy and be healthy. Bye bye.